one atom and it divides into two. So fission is division.
Chain reaction.
Fusion is a union of two or more atoms into one. Fission is a chain reaction, as we said, as you said. Fission is used in nuclear power plants. That's a reaction nuclear power plants go through.
What was that?
Fission.
Fission.
Yes. Right? What else do we need to know about that?
Nuclear power plants, what else? Mr. Greg.
Mr. Greg.
Yeah.
What do we got?
We're doing a review session now.
Review?
Yeah,
Oh, all right.
they are.
And then they don't work on me.
I don't know.
Look, it's me, Rishi.
They're okay. Yeah. Yeah, it's not going to be anything crazy about that.
That's what we need to know about.
Nuclear power plants?
There's division.
If I gave you like a diagram and pointed to different parts of that, like nuclear power plant thing,
Like
the diagram,
Cool.
you know what I'm pointing to?
Can you draw it and I'll tell you if I'm on
Great.
Oh, yeah,
Like this?
Stuff like the control rods.
Yeah, the control rods, you know about that?
Okay,
that's the reactor.
Yeah, that's a reactor, and then that gets fed into this thing right
Do we have to
here.
like draw it ourselves?
And then,
or-
no, you don't need to draw it
So
yourselves.
we want like multiple choice stuff? Or like
Yeah.
short
There's a couple of
Are we
them.
gonna name it?
It does.
Is this a fist or something?
It's called pumpkin and teapot.
Yeah, that looks
It
Oh, I
doesn't-
remember this.
That's the turbine.
That's a turbine, and then we got the water right
And
here.
the airflow.
Water, and then this steam makes it
The steam makes it all turn, and then it goes and
Back in,
condenses back into here, and it circles around.
That's what we need,
This-
no?
and it's a
That goes right there.
That's what we
Now,
need.
that's what you need
I
to know.
wonder if the water there gets.
You don't need to draw that. You just need to recognize
Okay.
what's going on here.
That's the reactor that heats up the water boils, steam, generates the turbine, and then it recycles.
That's right.
Did our class know this?
Yeah, we did really briefly.
So we do have to know this.
Maybe. Maybe. I haven't decided yet. Let's see. Yeah, so that's fission. That's a fission reaction. Fusion, is that more or less energy that's released?
More.
More.
It's only 0.7. 1. Not a huge amount.
That's fission right there. Yeah.
Basically,
So, if I give you a problem with like E equals MC squared, and I say, for instance, if I say that, tell me the amount of energy that's released. Tell me the amount of energy that's released.
Wait, you told us what we need
Tell
to
me
know.
the amount of
Oh, I
energy that's
know this.
released.
I know
You
this.
told us what we need to know for fission. What about fusion?
Tell me
Wait.
the
What
amount
do
of
you know about
energy.
it?
You're very demanding of a man, aren't you?
You're shooting. We already did fission and fusion.
Alright.
Yeah, but I feel like that we didn't talk about. We didn't talk about fusion. 0.1 and 0.7. It's a union. That's all we have.
That's all we have so far.
Fusion is a union.
So like
I'll
fission is.
just wait for a second. I'll wait for us to calm down.
What?
Yay.
Is it?
Me.
So a fusion reaction. A fusion reaction is a union of two or more atoms together into one. Now, this reaction converts 0.7% of its mass into energy, pure energy. That's fusion.
I know that.
Okay, it's different than
Fission is
Fission.
0.1.
it's
I did my project.
0.1. That's right. So if you have a mass, let's say your total mass, let's say you've got lots of material to use in this reaction. Let's say you've got 9,000 kilograms, and they're going to be in the units of kilograms here. Let's say you've got 9,000 kilograms. And this fuel is going to undergo, let's say, a fusion reaction. So it undergoes fusion. So how much of this mass is going to be used in this equation to get you lots of energy? Well, you'd figure out, well, since fusion takes 0.7% of its total mass and turns that into energy, you can figure out what 0.7% of this mass is. So you take 9,000 kilograms times 0.7, and that turns out to be, I don't know, but it's a number. 7 times 9 is
No, wait, what about speed of light?
60. What is that?
Wait, when you say
63.
numbers,
Mr. Sand.
That, right?
Wait, what about speed of light? Don't we use that?
Hold on. Hold on. So that's the amount so far, right? Is that correct? I think it is. 0.7% of this. Is that right? No, it's only 63, right?
No, yeah, because when you have to change 0.7% into a decimal, so like divide it by 100,
Whoa, I'm sorry.
because there's 0.7%.
and then
Oh, you're right. You're totally right. I'm sorry. Yes. Whoops. That's a big mistake right there.
Oh.
It's a big mistake by Mr. Sand. Sorry. So
Oh,
it's
yeah.
0.007. That what the total amount of that is going to be
Wait, why is it
63.
6.3, right?
No, 63.
You sure?
Yeah.
Okay. 63 kilograms.
And what is that?
Okay, so now this is the amount of mass. Think about what we've got right now. That's the amount of mass that is going to be turned into. That's what I thought.
No,
Thanks.
it's 63.
It's
What?
63.
Wait, how
Try it
many-
again. 0.007 times 9,000. Yeah.
No, wait. No, you did it wrong.
No, I didn't. What?
Oh, let's fight.
What?
You did 900.
It's 900. It's,
It's
not
9,000.
9,000. Oh, JK.
Oh, JK is right.
You should say we'll do.
Oh, Rishi got it. Okay, 63 kilograms. That's the amount of mass that's turned into pure energy. Just pure energy. That's crazy.
That's a cray.
Now, let's put that into this equation to get our pure energy that's out of this reaction. Let's do it. So, let's do it. We got this 63 kilograms, and now we're going to take this times, what is it? It's 3e, and then that's squared. Oh my god. That's going to be 9e to the 16th. That's what this is. Okay, so it's 63 kilograms times 9e, and that's meters per second. So this turns out to be joules, right? Whatever 63 times that is, it's going to be a huge number.
Wait, isn't 8 squared 64?
8 squared.
Isn't it 8?
No, when it's e to the 8 raised to the second power, that means it's.
Oh, it's an exponent.
It's
It's
right.
5.67 E60.
It's the way you wrote it, right?
No, it's wait, what? What do you?
I don't know. You told me something.
Yeah, it's
5.67
5.67 E to the 8.
Okay, so let's think about sig figs here.
Joules.
Oh my god, let's make this significant. Let's make that significant. Let's make this more significant. Because I just made this up.
with the percent.
There. Okay, now it's good.
360.
Haha.
That's a bad word.
Yeah.
With the percent, like 2.7%, and then when you're saying
That's for joules. Joules.
Yeah, this is joules.
Do we go?
What? I'm sorry.
with the 0.7%, then when you're saying
I'm just saying let's make this like that. Let's
so
make
you
it.
would like tell us.
Yeah,
Okay.
So we have to like do
I think I do. Oh, I don't say that. Yes, don't let that limit your sig figs, okay? Alright, that's fusion. Fission, it would be 0.001. Okay. That's equals mv squared. The last thing we need to do is the very last thing, and thank God, because right now we're at 53 minutes. Can you believe that? We've been having fun for 53 minutes.
Even if there are 4 sig figs, why is there 4? Then the answer, it was 5.67 equals the 18th.
The e to the 18th is not, that's not significant. It's 5.67. There's only 3 sig figs there.
But don't we have 4 sig figs in 9,000?
Yeah, but it's multiplied by this, which is, oh, you're right.
But
Yeah, I mean,
okay.
I'm trying to get us through this fast.
Wait,
So I'll make sure it's very clear for you. I like that you're asking that question. That's a good question to ask. You're right, it would be 4 sig figs, so the final answer should be 4 sig figs for that, okay? So that's a good question to ask.
We have the energy, we have to find the mass.
Yeah.
What?
Rishi just asked, is that kind of question going to be on the test? And I said yes.
No, so I said something about
No, he asked this differently, but that's basically what he said. Yeah, Leticia. Did we go over that? No. Okay, the last thing is E equals hc over lambda. Here's a big spoiler alert. Maybe I shouldn't tell you guys this.
No, you should.
Mr. Shine. Come on.
Don't tell your friends because they didn't come.
Alright.
E equals, we should do other things. Oh, this is all blanked out. Oh my god.
Do it!
What a jerk. Okay. Okay. You can see that these two equations, like I said this in class,
They
I
are the
said it in one of
same.
the classes, they both are set equal to E. So what you can do is you can set them equal to each other. Oh my god, what happens there? You got hc equals, or hc over lambda. So that part equals that part, hf. So if this happens, then it's going to be like, this will cancel out, right? So it'll be c over lambda equals f. So if you have one of these things, like lambda, you can figure out frequency pretty easily. This requires you to think on your feet. I'm just saying, oh, that's it. That's all you get. That's all you get. No more.
Whoa.
No more.
I didn't get to copy.
Come on. See, exactly. I don't want you to copy it.
Like,
This is
give
for.
us a problem with one of these equations, we can just like merge them together and figure it out.
Yeah, it's going to be one of those thinking problems where you have to kind of think about what's given to you.
Use this problem for both problems.
Those formulas will help you solve lots of different kinds of problems. Okay, so let me tell you, let me be a little bit more clear and less cryptic here, okay? Now I'm a little bit less happy that you came. Right. So I would like to get this moving right now. We've got the last kind of problem is this energy released when an electron goes from a higher energy state to a lower energy state. And we use these equations. We use E equals hc over lambda for these kinds of equations. We also use this right here. I give you this. I give you this. You need to tell me things like what is the energy and what is the wavelength of that light. If I give you one of these things, you can find the other. This isn't anything crazy here. I'm saying, like, if there's a question that says, if you've got, let's just say it's 410 nanometers. That's the wavelength of light that's given off. Okay, let's say that you heated up something like in the flame lab, and it gives you this wavelength of light. This turns out to be purple light. So you heat something up and it turns out to be purple. Well, you can tell me what that energy is in joules of that light that's given off. Well, how do you do that, Mr. Sam? Well, let me tell you. You first have to convert this. I know this was quick today. Convert this to meters, and then you can put that into that equation right there and figure out what the energy is. Because this is a constant, that is a constant. You don't need to do anything with those. You don't need to find those. They just are given to you.
Wait, can you put it in terms of that? Can you put it hc over the number of meters equals energy? Or do you actually calculate it?
You put that in your calculator, and then you find out what the energy is.
Why does it have to be what's
Because that's what these constants are set for, meters. So to convert this into meters, it's very simple. You just take 410 nanometers, and then you take, oh my god, how many nanometers are in a meter?
So 1 meter over 1,000. Or is it 1 million?
I believe it's a 9, right?
Oh, really?
I'm pretty sure.
Oh yeah, nano is a million.
Yeah.
A billion.
Can we do a billion six?
Okay.
No, billion's 9.
So that's how you turn it into meters, and then whatever this is, you put it back into this little equation, and these are all constants. You can figure out what the energy is. Vice versa, you can figure out what the wavelength is if I give you the energy. And if I give you energy over here and I ask for the frequency,
How did you figure out the wavelength if you have